Welcome back, AP Chemistry. I am Miss Palchik again. This is a continuation of our 1.3 and 1.4 composition of pure substances and mixtures. One of the things we have to talk about is empirical molecular formulas. There was one year, right, 24, 25, that we did not cover empirical formulas in class. So if you took chemistry during that time, you may not remember this, and most of the times, students a lot of times forget this anyways. So I think this will be a good refresher if you did study it, and if you have not, if this is your first exposure to it, we'll go through it together as well. All right, so an empirical formula is the lowest term ratio, right? So all of the subscripts are in its lowest terms. All ionic compounds are empirical formulas. Okay, a molecular formula is what's in the actual molecule. So a lot of ionic compounds, their molecular and empirical formulas are the exact same. There's a lot of covalent compounds, however, that their molecular formula is different than their empirical formula. All right, so if we look at a few here, we have hydrogen peroxide, ethylene, and dextrose and water. Right, here are the molecular formulas. So hydrogen peroxide is H2O2, ethylene is C2H4, dextrose is C6H12O6, water is H2O. Okay, all of those are molecular formulas. That's what the actual molecules are. However, not all of these are empirical formulas, right? Empirical formulas are the lowest term ratio. So because I can reduce these, its empirical formula is really just HO, right? I can reduce these, CH2. I can reduce this, CH2O. Water I can't reduce. So its empirical and molecular formula are the same of H2O. Okay, we are going to look at how to calculate molecular formulas from some given lab data. Okay, so it says I have the sample of caffeine. It was analyzed. It contains 49.5% of carbon, 28.9% nitrogen, 16.5% oxygen, and 5.1% hydrogen by mass. I want to know what is the molecular formula. Okay, well, the first thing I want to do is I want to assume that I have 100-gram sample. Sorry, I thought I had something else in here. Okay, it must be in the next one. So I am going to take, and what that does for me is it takes all of these things that are in percentages and it just changes them to grams, right? If I had 100% and I had 100 grams, I would have 49.5 grams of carbon, right? 28.9 grams of nitrogen. It just makes the numbers a little bit easier to work with. Ooh, boom, here's the step I wanted. Sorry, these should be switched. It's good. All right, so the first step I'm going to do is I'm going to assume that I have a 100-gram sample. You just saw how I did that. Real easy. All right, I'm going to take those masses and I'm going to convert them to moles. I'm going to divide by the smallest one, and we'll talk about why. Okay, and if they're not whole numbers, I'm going to multiply by some factor. All right, there's a couple examples there. And then I'm going to use the molar mass of the compound to kind of determine my factor of how does the empirical and molecular formula relate to another, right? In the previous slides on that table, right, we saw that with like dextrose, it was a factor of 6 that they all had to be multiplied by, right? Ethylene was just a multiplication of 2. So it kind of depends on what it's going to be. Okay, so I assumed my 100 grams, right? Did that step, bloop, 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 right? Now I'm going to convert it to moles, right? Well, I can use the mass off the periodic table, right? So if I have this many grams of carbon, I can figure out how many moles of carbon I have, right? Same thing with nitrogen, oxygen, and hydrogen. All right, when I do this, I get all of these lovely number of moles. So here's how all the number of moles compare to one another. Okay, this mole ratio is typically what we see as a subscript in our formulas. However, we never see formulas with like 4.12, 2.06, right? We don't have decimal points in those subscripts. So what we have to do is we have to divide by the smallest, and that'll help us get these into whole number ratios, right? So since 1.03 is our lowest number of moles, I'm going to divide every single one of these by 1.03. When I do that, I get 4, 2, 1, and 5. Boom. Whole numbers. They're beautiful. I love it. Okay, these are now the subscripts for my empirical formula. So my empirical formula for caffeine, I know is C4H5N2O. Right, that is my empirical formula. So now what I have to do is I have to say, okay, if this is my empirical formula, how does that match up to they told me it's caffeine? Is that caffeine's, what do I know about caffeine? Right, I don't know the formula. Well, I can take my empirical formula and I can find its mass. Right, it's 97.10. Great. right? Did the C times 4, blah, 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 all the good stuff. Well, I know that it's caffeine. I can look up the mass of caffeine. I can see that it's 194.2. So how do these two compare, right? Well, if caffeine is 194.2 and my empirical formula is a 97.10, I know that this must be a factor of 2. So to get to my molecular formula, I have to multiply all of my subscripts by a factor of 2. So caffeine's molecular formula is C8H10N4O2, right? All of these numbers got multiplied by a factor of 2 because I need 2 of these masses to get to this guy. Okay. Let's keep going. There is one of the reactions we studied was combustion reactions, right? And you can analyze these to figure out what is the fuel that we're actually burning, right? So what they do is they put the fuel into this chamber, right? Here's like a little furnace. Oxygen goes in. It's free to react. So here's our fuel plus the oxygen. When it comes out, it's going to figure out how much water is absorbed and how much CO2 is absorbed. Okay, so remember, the fuel here, one of the big things is that it's made up of C, H, possibly O. Okay, but if we look, our C and our H only end up in one place. So let's say that I have this guy. I have 2.04 grams of a sample. It's made of CH and O. I threw it through the combustion chamber, right? I figured out that I can make 4.48 grams of carbon dioxide and 2.4 grams of water. Okay, we have to determine the empirical formula from this. Well, because that fuel is my only source of carbon and my only source of hydrogen, and because my carbon and hydrogen end up in different spots, they're never together, I can use some quick stoichiometry to help me figure this out, right? So I can say, okay, so if I have 4.48 grams of carbon dioxide, I can figure out how many moles it is, I can figure out how many moles of carbon that is, and I can figure out how many grams of carbon that is. Right? Same thing with water, 2.4 moles of water to moles of hydrogen, 2 grams of hydrogen. I copied that and didn't change that. Imagine this is 1.07. Okay, great. So when I do this math with this correct number, I'm going to get 1.22 grams of carbon and 0.02 grams of hydrogen. Okay, so I can figure out, okay, so if I made this much carbon dioxide, that must mean that all of this carbon came from this fuel, and that's how much it was, right? If I made this much hydrogen, all of that hydrogen came from this hydrocarbon, and that's how much it was. So if my total fuel mass, if I'm looking to figure it out, right, I know that it's made up of CH and O. I know the mass of C now. I know the mass of H. I just have to do some quick math and figure out the mass of oxygen. Right, so they told me it's 2.04. I calculated these out. I just need to figure out how much oxygen was in there. All right, that should be the final part of assignment 2. Again, if you have questions, let me know.